Hi! This is a crazy headlamp for a car. Its light source is not a halogen bulb or an LED. It is a laser. In this video, I will take a closer look at how this beast works and how to make it work. After figuring out how to power its sensitive laser diode, I will measure its optical power output. How strong is this laser meant to be put into a car? Let's find out. When experimenting with a laser, wear safety glasses suitable for its wavelength and power output. And never look directly into a high-power LED or LEP. This headlamp is sold on eBay without any power supply, so my first challenge is to find a suitable driver, since laser diodes are very easily damaged. Would be sad to destroy a $69 light within seconds. Luckily, the listing came with some clues on how to power it up. It uses a 450nm laser at the border between indigo and blue and can handle up to 3 amperes. Quite a lot of amps for a single diode. But I found this driver board that will deliver a constant current of up to 4 amps to a blue laser diode. Nice! However, I have never bought a laser diode and driver separately and matched them up. How do I make sure this driver will not deliver more than 3 amps? To get some hands-on experience, I will take it step by step. The issue is, laser diodes have a bad behavior called negative temperature coefficient. In short, they decrease their resistance as their temperature increases. This will lead to a destructive thermal runaway when they draw more and more current as they heat up. The best way to stop this vicious circle is to use a constant current power supply. Limit how much current the laser diode is allowed to draw. Alright, first step in my needed hands-on experience will be a simple one. Set up the multimeter to read a current of 3 amps DC and adjust a constant current power supply to 3 amps. As a dummy load, I will use a resistor with around the same resistance as the laser headlamp run at max. I will not limit the voltage. I will only limit the current and let Ohm's law take care of the rest. There we are. The circuit is now set to 3 amps with milliamps precision, without blowing anything up. But this was way too easy. Unlike a laser diode, this resistor does not have an NTC or electrical polarity. Next step in the challenge is to use light-emitting diodes. Just like laser diodes, they do have an NTC and electrical polarity. This mess is for high-power LEDs wired in parallel. Each LED will handle 750 milliamps, so in parallel they can handle 3 amps in total. Perfect. After double-checking correct polarity, plus to plus, and setting the power supply to constant current, let's see what 3 amps will do to this circuit. Okay, they are already getting bright. I will diffuse them to spare my eyes and camera. Success! The LEDs are fully powered up under conditions that are very similar to what the laser headlamp needs to run at full power. The power supply is providing 4.1 volts to the circuit. You might think it is a bit high for LEDs listed as 3.2 to 3.8 volts. But I am not worried because the current is right for the LEDs and there is a voltage drop across the multimeter, known as burden voltage. The forward voltage across the LEDs is not the full 4.1 volts. I can simply show it by removing the multimeter from the circuit. This time with glass for welding mask over the LEDs to see all of them light up. 3.8 volts within specs. Makes sense the voltage is at the high end as there is plenty of cooling for the LEDs. Keeping them cool keeps the resistance at their high end, which in turn means a higher voltage is needed to push 3 amps through the circuit. At this point, it is tempting to just replace the LEDs with the laser. But laser diodes are way more sensitive than LEDs, and this switch mode power supply does not deliver a clean current. Switch mode is inherently noisy with ripples in the output. I don't trust this power supply to safely run a laser diode, especially at startup and shutdown. This is where the laser driver board comes in. It is designed to deliver laser-friendly electricity. The driver will run on anything between 9 to 10 volts DC. I could use a battery, but I already have a power supply on the table. Just need to change it from limiting current to limiting voltage. I will set it to max 9 volts. Should be plenty enough, as the driver board only needs to output around 4 volts to the LEDs or laser headlamp. Before hooking up the driver board, I have dialed its current limiter all the way down. I am using a trimmer tool since it is sleeved, making it less likely that the tool slides off and short-circuits something while I am looking at the multimeter to dial in the current. The potentiometer does not seem to have a hard stop, but it starts ticking when dialed all the way down. After making sure I got all the polarities right, it is time to test the driver. Great start. At 81 milliamps, the LEDs are already lit up. Time to see if this tiny driver will deliver 3 amps. Did I break it already? Nope. The current is climbing now. This type of potentiometer really takes a lot of turns, useful for higher precision. Nice! This will deliver 3 amps at around 4 volts. Time to test the laser, after resetting the driver to minimum and after this short message. A big thanks to all my patrons. I appreciate your help with keeping these videos like this one coming. For just $1 a month, you can help me out too and get full access to all my posts on patreon.com. Link in the description. Thank you. Okay, after having built up a proper setup step by step and getting a feel for the current adjustments, I am ready to power up the laser headlamp. Only one more precaution to take care of. Laser diodes are destroyed by electrostatic discharges. I will therefore baby the headlamp at a static-free workstation until I have it connected. I will also make sure the driver does not have any remaining charge in an output capacitor. That would dump too much unregulated current into the laser once connected. Good, no charge remaining. I will attach the laser while making sure plus goes to plus. With laser safety glasses on, I am finally ready to power it on. Will it work? Oh yes, even at lowest driver setting, I am already seeing white light. The laser is shining its blue light down on a phosphor that converts some of it to other colors of light. This is known as LEP, Laser Excited Phosphor. Let's give it some more juice. Okay, I am not sure this is good for my camera sensor. Let me diffuse the light. Wow, this is intensely bright. Hard to see on the overexposed camera, but most of the light is in a tight, bright beam. How strong is the laser in this headlamp? Definitely stronger than my temporary cooling solution can handle. I need to find some M2 screws to add heatsinks to the back of the lamp. For short runs it is fine though. To double check, I'm running the laser diode within specs. I measured the voltage from the driver. 4.3 volts, including the multimeter driven in series. That is fine. The power loss in the driver is around 3 watts. A small cooling fan on the heatsink might be a good idea for long runs once I have proper cooling on the laser diode. Regarding power, the specifications do not mention the optical power output of the laser. I believe there are some hidden clues though, suggesting a laser around 3900 milliwatts. Really? That's a very strong laser. Almost 3 times stronger than my Arctic laser. Almost 8 times stronger than the threshold for class 4 lasers, the highest laser risk class. I must be reading the specs wrongly. Well, only one way to find out. Measure it on a laser power meter. To gain access to the laser beam, I will remove the bottom plate with the phosphor on it. A Torx T6 bit will do the job. There we go. Don't lose the tiny lock washers, even though they are magnetic, in case you need to find them on the floor like I had to. The laser beam is reflected straight down onto the phosphor by a mirror placed at a 45 degrees angle in front of the laser aperture. Some laser power will be lost to this mirror in the optical path. A first surface mirror will reflect around 95% or so. Only a 5% loss, but worth keeping in mind. Now, before the final test, I would like to tell you about a much more sophisticated piece of electronics for measuring high energy photons, made by the sponsor of this video. This is the RadiaCode radiation detector, a tiny device packed with features that old-fashioned Geiger counters can only dream of. Not only is it a detector and precise dosimeter, it is also a gamma spectrometer with isotope identification as demonstrated in an earlier video. Another feature is its radiation mapping. When paired with your smartphone, the RadiaCode can map the radiation levels on your path. You might discover exciting radiation levels on your walk or shopping trip. For example, from granite buildings and tiles, or that special uranium glass and glaze in the thrift shop. Finding radiation sources can add some spice to an otherwise ordinary travel. For much more information, I recommend you check out their website, link in the description. Use the promo code BRAINIAC75 to take advantage of a special offer from RadiaCode. Details are in the video description. Thanks RadiaCode for making a difference and helping out my channel. Now back to the laser radiation. Alright. With laser safety glasses on and the laser power meter calibrated for 450 nanometers, we will now find out if this is around 3700 milliwatts after mirror loss. That's a lot of photons. It peaked at 4370 milliwatts after mirror reflection, likely 4600 milliwatts before the mirror. Wow! To make things even crazier, the listing says the 3 amps limit is not due to the laser diode. It is the phosphor that will give up first if the laser is dialed higher. Astonishing! Click like if this laser excites you as much as me and the phosphor. In my next video, I'll test this little gem further and compare it with a cheaper LED headlamp. Remember to subscribe and turn on the full notification bell if you don't want to miss that video. And comment if you have ideas for further testing of the headlamps. In any case, thanks for watching. Bye for now.